Um, it's a privilege for me to speak here because this is my alma mater. I did my MSc degree from here. All of you can hear me? Even without mic, I think it should be okay. So I finished here in 1975. At that time, this wing was not there. We only had a C-shaped building. Yeah. I'll present two talks, one now and one in the afternoon. And because of my background, I will stick to optical devices, optics, and also say a little bit of nonlinear optics, fiber optics. Okay. I must confess that I don't have a great expertise on quantum optics. When Dr. Sridhar asked me to speak here, luckily I had two review articles with me, very recent. One is in this year and the other is 2023. So from that I thought I should present this talk. This is more on devices. Yesterday you had very many excellent lectures on the theory of quantum optics and so on. So my talk here will be pretty qualitative, so excuse me for that. I will share the review article which I have consulted to prepare my PPT. Any one of you is most welcome to copy it later, and in case you feel like interacting more, my email address is there. I'll be happy to answer any questions. So the first talk which I'm going to present is optical fibers for quantum communication, or quantum applications rather. All of you know about optical fibers. Am I correct? Most of our telephone conversation is through optical fiber communication. So this is pretty old. Optical communication started in 1970s when the first high quality fiber was fabricated in 1970, around that time. 10 years before that, laser was invented. So communication became possible and it emerged in a big way after 1970. So this talk will focus on certain fiber devices which we now think we can employ for quantum communication or quantum computers. And I will in particular focus on sources of the light which is employed for quantum computing. So this is my focus for this lecture. And continuing with this, in the next lecture, I will present some details about how to generate coherent radiation at terahertz frequencies. Why terahertz frequencies, I will tell you in the next lecture. Okay. So this talk is mostly on visible light, infrared, which is used for optical communication. Okay. In between, if you have any questions, you can raise your hand. I'll be most happy to answer them. Okay. How do I change the slides from here? Or should I use this? ಇಲ್ಲಿ ಪಾಯಿಂಟ್ ಮಾಡೋದು ಇದೆಯಾ?
ಗೊತ್ತಾಗ್ತಿಲ್ವಾ? ಸೆನ್ಸರ್ ಆಗ್ತಿಲ್ವಾ? ಇಲ್ಲಿ
ಅಲ್ಲಿಂದ ಮಾಡ್ಬೋದಾ ಕೀಬೋರ್ಡ್ ಇಂದ? ಕೀಬೋರ್ಡ್ ಇಂದ ಆಗೋದಾದ್ರೂ So as you might have realized, this So my talk will focus on photons. See, quantum computing in particular or measurements can be done in several ways using electron spin states and so on. My focus will be on photons. By the way, photons are the most quantum mechanical objects that we know of, because it is generated, visible photons are generated by transitions. So the quantum nature is inbuilt into photons. So that is something which we keep in mind. The main areas in which quantum applications are focusing right now is on quantum computing, quantum communication, and measurements, particularly for sensing. So making sensors, very sensitive sensors. So these are the areas which we can look at. By the way, whatever I am saying there, presenting here is there in the review article. I have put the review article at the end of this PPT, and you are most welcome. The full article is there. You can copy it from there, okay, if you want. So emerging technologies are like quantum computing, secure communication. We all understand what is secure communication. Do we? Secure communication. What would secure communication mean? Communication which cannot be, picked up by somebody else. Okay. So it turns out that if you have wireless communication, it is always possible for the others to pick it up. Or even if it is fiber optic, because you need converters, detectors, and so on. Nowadays, different countries want to eavesdrop or listen to what is happening in other countries. So it is possible for people to listen to what you are talking, what you are saying. To prevent that is the motivation for quantum secure communication. There are techniques to do that. I will not focus more on that. In fact, very high sensitivity measurements can be made by quantum techniques, quantum photonic techniques. What is an example? LIGO. You are aware of LIGO, right? What is LIGO? It's a Michelson interferometer with very long arms. How many kilometers? I don't know the distance in kilometers, maybe 10, 20 kilometers each arm. 4 kilometers. If you have worked with Michelson interferometer in the lab, you will realize how difficult it would be to form the fringes, particularly if the distances are so large. Because one thing you have to ensure is the coherence of the light has to be good enough for that kind of distance. Even if you are short distance, working with Michelson interferometer takes some skill. So this thing called LIGO is a very, very sensitive measurement. Perhaps you know that. Because what does it detect? It detects waves generated by fluctuations in the gravitational field, huge gravitational fields which surround these supernova and so on. Supernova explosion is supposed to generate gravity waves. So it is so weak that by the time it reaches the Earth, it will have weakened to such an extent that it's very hard to measure. And only recently people have measured that. Okay. This sensitivity is also exploited in sensing applications. Like you are aware of MRI, magnetic resonance technique for detecting, issues with the human cell. You use a squid detector in that. What is a squid? It is a superconducting sensor. It has to be maintained at a very low temperature. So that is also a very sensitive measurement. It's not easy to study the small changes which happen in human cells otherwise. So this is similar photonic techniques, quantum photonic techniques can help you to make some measurements which are very, very accurate. Okay. What is used in these systems? Certainly light is used because we are talking about photonics. you can have, one is trying to visualize a optical computer, okay, quantum optical computer. So basically we are to deal with light, and in my talk, if you are dealing with communication systems, not only do we need source of light and detector of light, we also need other components which will mix the light, process the light, okay, and then carry it from one node to another node. So lot many other components are also needed if you want to build a photonic network. Okay, so I will not really focus much on the long distance communication, but I will focus on how to generate these photons and how to detect them. Okay, so efficient systems for photon generation. In a computer, you know that there is storage, memory. You also have what is called a switching in computers or in any electronic circuit as well. Multiplexing. Anybody knows what is multiplexing? Multiplexing is mixing of two or many more signal streams. First thing is for you to know is that digital data communication is executed in terms of bits, zeros and ones. This you know, right? Couple of zeros and bits form a byte, and then you form a word that is pushed through the channel, received at the other end. It is not like in the olden days. Olden days there used to be radio communication or telegraph lines, but now it is all optical fiber communication where digital techniques are employed. Okay, so in the motivation in any communication system is to maximize the amount of data that you can send through these channels. Okay. So for instance, if I have a single fiber, optical fiber, through which I want to send data from say Mysore to Bangalore, for a given condition, you can send only so many bits per second, maybe 10 gigabits per second, or maybe 20 gigabits per second. This happens for a particular mode or for a particular type of bit generation. Okay. For instance, one parameter could be the wavelength. The concept is the following. Suppose you have a beam of light of a particular wavelength or frequency. Chop it, make it into bits. Okay. You can chop it so that one bit has low intensity, the other has high intensity at the same wavelength. So these are the optical bits. If you are operating at a particular wavelength and sending information through one fiber, there's a maximum that you can do, maximum number of bits which you can transfer. Okay, but this may not be sufficient for many things like sending a picture, maybe okay for voice communication. Okay, so what do? What people do is they do something called multiplexing, which means I have two different streams of bits or bytes. I merge them. I may have more than two, maybe 10. Merge them, put it into a single fiber or a single transmission channel. This process is called multiplexing. And there are two different types of multiplexing. One is called time division multiplexing, and the other is called wavelength division or frequency division multiplexing. Okay, we will not go into details of that. If you see some books, you will get the details. But this is a technique to increase the data transmission rate in the same fiber. So for instance, suppose you have one stream at wavelength lambda 1, one stream of data, another stream of data at wavelength lambda 2, another at lambda 3. You can send all the three streams through a single fiber without them intermixing or crosstalk. Okay, so this is the essence of multiplexing. And of course, in any system measurement or communication system, you have to do some processing, okay, detection, amplification, mixing. Optical fibers are widely used in general communication system. Optical fibers of a particular type are also are being developed for quantum communication also. What is the difference? I will tell you. Okay. So, I will show you a slide where it's a kind of a schematic of a optical communication, optical fiber network, where you will see different components. It's just a matter of information for you. So, in any such system, there are multiple items which are present, like an electronic circuit for the detection process, an electronic circuit for driving the laser. There can be a photonic chip, and there can be other things like a resonator and so on. Okay. So, in such a system, you have to put all of them together to achieve a certain goal. Okay. So, that's what I have stated here. Optical systems for quantum applications require integration of electronic chips, optical components, and miniaturized optical chips also. We have something called photonic integrated chips, which do a certain type of function. All those things have to be put together to make a system that may form one node. From one node to another node, you have to transmit these signals. Okay, so generally this is what we will try to understand today. So devices such as laser diodes, memory elements, optical switches and so on, they have to be there in the system, and they can work at different wavelengths. You may have a source at a certain wavelength. You may want to convert the frequency in between for some purpose. The detector may be working at may have maximum sensitivity at certain wavelength. So these photonic systems have to work at different wavelengths. Okay. So we need to have components which are able to manage to work with multiple wavelengths, multiple device types, multiple wavelengths. Okay. And the wavelengths can stretch from maybe deep blue, ultraviolet, all the way up till near infrared. Just for your information, optical communication, which is all these optical fibers, they use laser at a wavelength of 1.33 micron or 1330 nanometers and 1550 nanometers. There are two wavelengths which are preferred in optical fiber communication, 1330 and 1550. Of course, it may be 1552, 1335. Why are these wavelengths important? 1330 is important because that is the wavelength at which pulse broadening or dispersion effects are minimum. Okay. Why is dispersion important? Dispersion is important for the following reason. You create a byte by putting in 8 bits, as far as I know. Some people may be doing by putting 16 bits or 32 bits. Okay. So as an example, we take that say A is expressed as 8 bits. Okay. We'll have a certain code which will mean A. B will be represented by a certain another bunch of 8 bits in which zeros and ones are arranged in different combination, right? These bits are separated in time. One pulse comes after the other pulse and after the other pulse. So there is a certain time gap between successive pulses. So what happens when such a digitized signal goes through a communication channel, whether it is optics or microwaves, the situation is the same. These pulses broaden. Okay, they spread out in time. So if these bits spread out in time too much, neighboring pulses can mix. If they mix, we call it corruption of data. I hope you are following. Okay, so that should be avoided. If you want to avoid that, you have to design your transmission channel appropriately, or choose a channel in which this spreading or dispersion, what we call as dispersion, is minimum. Okay, so as far as communication channels are concerned, two things are important. The dispersion of the channel should be minimum, and the absorption of energy in the channel should also be pretty low, so that you can reach a larger distance. If the dispersion is less, you can send more data. Okay, so the amount of data that you can send through an optical fiber or a channel depends on how much is the dispersion in the fiber or the transmission channel. Okay, so that is why dispersion is important. You will see that the type of fibers which are used for optical communication, conventional optical does not work for photonic communication. Okay, we'll see what is the new type of fiber. Okay, so what we see is that for using in photonic systems, what are called as microstructured fibers are used. What is a microstructured fiber? I will elaborate shortly. Okay. Microstructured fibers are also called photonic crystal fibers. So that word crystal will ring some bells. We have dealt with, you deal with crystal structure in your condensed matter physics or solid state physics. So you have some understanding of band gap formation and so on. Okay, such a concept is extended to optical transmission through a fiber, and similar, stop gap. There is a set of frequencies which are allowed to be transmitted. Certain frequencies are blocked. Okay, just like you have conduction and valence band separated by a band gap, right? Conventional optical fibers, by conventional what I mean is whatever is installed in our city and near our homes. Okay, they are of basically three types. One type is called single mode fiber, the other is called multimode fiber, and the third variety is called graded index fiber. For your information, if I want to send a signal from Mysore to Bangalore or Bangalore to Delhi, for the intercity link, we always prefer to use single mode fiber. Okay, why single mode fiber? Because in that the amount of dispersion is much less than in the case of multimode fiber. Okay, but single mode fibers are more expensive because they are more difficult to fabricate. So for short distance, so within this building or from your building to the Vice Chancellor's office, you can afford to use a multimode fiber. Multimode fibers are cheaper, and you can transfer sufficient data at a sufficient rate from here to your library or the Vice Chancellor's office. Okay, so the choice of fiber depends on the application. Long distance communication, you always use single mode fiber. Okay, these graded index fibers are different from either a single mode fiber or a multimode fiber in the following sense. You know that every fiber has a central portion called the core. Fibers are like cylindrical wires. Central portion has a little higher refractive index than the outer portion. So you call it a core, and surrounding the core, the glass portion surrounding the core is called cladding. Generally, the core diameter is much less than the size of thickness of the cladding. Okay, I will show you the numbers. Okay, but in a multimode fiber and a single mode fiber, the refractive index difference the refractive index changes only at the boundary of the core. So it is called a step index fiber. The refractive index changes from a high to low exactly at the boundary of the core. So it's like if you plot the refractive index versus radius, starting from 0, which is the axis of the fiber, refractive index goes like that and then comes down and settles down at the level of core refractive index. So this is like a step, so it is called step index fiber. In the case of graded index fiber, cladding refractive index is at a certain level. In the core, it has to be higher. It doesn't stay, rise like a step, rises gradually. Okay, so the refractive index distribution is variation with radius is continuous, not a step. There are advantages if you make fibers of that kind, but obviously it is more difficult because you have to gradually change the refractive index. Fabrication process is a little more intricate. Okay, so these are the three types of optical fibers which are employed normally. And however, yeah.
Graded index also. There are two varieties, single mode and multi-mode.
Graded index are all more or less. See, what happens there is there are multi-mode, but the grading of the index is such that the pulse broadening is much less than in a step index fiber, because essentially the path lengths within the graded portion for different modes are such that they start from one point, which means all of them have the same position at that point in the fiber, and then they spread out. Speeds are different, so they arrive at another point at the same time. So if all the pulses are different wavelengths, they arrive at the same, or different modes arrive at the same point simultaneously, and we get a well-defined pulse, not a broadened pulse. So that way, in a graded index fiber, the pulse broadening is curtailed. Of course, there is a little bit of broadening; it cannot be avoided. Even with single mode fiber, there is broadening. Okay, right. So optical fibers have a core and a cladding. I told you that the core refractive index is slightly higher. How much higher? About 1%. So if the cladding is, see, optical fibers are made using pure silica. What is silica? Silicon dioxide. Okay, pure silicon dioxide. That is glass. Okay, so fibers are basically glass wires. What is the difference between the core and the cladding? The core is pure silica doped with certain oxides. When you mix these materials, the refractive index changes. So you add materials which will slightly increase the refractive index of the core. So these are well-known techniques, and people have perfected this art of making single and multi-mode fiber graded index fiber. They are easily available, and then low-cost fibers are available. Okay. So the difference between refractive index in the cladding and the core is roughly 1% or less. Okay, so this is because you want to reduce the, you want to ensure long distance transmission with reduced dispersion. Okay. If you look at the dimensions of the core and cladding, the single mode fiber has a smaller core, or a core of smaller diameter. Okay. Then I must tell you what is the meaning of modes. See, by modes, theoretically what we mean is eigensolutions. You understand the word eigensolution. You have learnt about quantum mechanics, right? H psi equal to E psi. You solve that for a particular system, you get psi n, E n psi n. Each psi n is supposed to be a mode. Can be said to be it is an eigenstate. Okay. So in optics also, if you transmit light through a waveguide, you can look upon the light which is traveling in the waveguide as a superposition of modes. Okay, just for your, as an example, if I transmit electromagnetic wave through a rectangular waveguide, metal waveguide which is has a cross section of a rectangle, so like a pipe. I want to transfer microwave energy, I'll take a pipe and push the radiation through the pipe. The radiation can be, whatever radiation is traveling through the waveguide can be decomposed. It's very much like quantum mechanics. If you have a general wave function, you can decompose the general wave function into a set of eigenfunctions, superposition of eigenfunctions of a system. See, like a harmonic oscillator. If you solve harmonic oscillator equation in quantum mechanics, you get the eigenstates. Okay, special states which satisfy the equation H psi is equal to E psi. Those solutions are very special. Please realize that. They are called eigenstates. And your Hilbert space, which we talked about yesterday, Hilbert space is assumed to be to have these vectors as the basis vectors. See, like ijk. In three-dimensional space, if I want to represent velocities, position and momentum and so on, I talk about the three components, which means space is three-dimensional. It has three unit vectors or three mutually orthogonal states. To solve the hydrogen atom or harmonic oscillator, the number of solutions is infinite. Okay, all those special solutions form a coordinate system kind of, with each state as a orthogonal vector. Okay, what is the use of this? The use of this is I know how to handle the eigen solutions. If I want to construct a more complex solution, I look at it as a superposition. Since I know how to handle each part, eigen solution 1, psi 1, psi 2, psi 3, I can construct the solution for a general psi also. That is the basic thing. It's like in mechanics. If you know how to work out the motion along x-axis, y-axis, z-axis, or the velocities, combine them and you get the total velocity, okay, or the total trajectory. So this is a concept which you should understand. In this context, I would also like to mention that Fourier analysis is very important, because when you expand a function in terms of Fourier series, each of those terms is basically like, it's like an expansion in some vector function space. Okay. So I was trying to tell you something about the dimensions of core and cladding. Single mode fiber, therefore, is a transmission channel in which only one mode will travel, and that is the so-called fundamental mode. Okay, amongst all the modes, you can identify what is called as a fundamental mode, which will always be excited, which will always exist if you pump power into that channel. Okay, it is like you have a system of atoms, many of them will be in ground state. So ground state is kind of ensured. Okay, so like that, the so-called fundamental mode will always exist in the transmission channel. If you construct the channel such that the other modes are either attenuated or not allowed to travel, then you have a single mode transmission. Okay. What is the advantage with a single mode transmission? The advantage is the following. For each mode, there is a certain dispersion. Okay. If you have multiple modes, there will be dispersion for each of them. So the dispersion will add up. Okay. If the dispersion adds up, what is the problem? The pulse will be broadened more. Okay. So now, if you have only one mode, you need to count the dispersion only at one mode. So that is the advantage with single mode. Why did I say this? Because in the fibers which we will discuss for quantum applications, these fibers are created so that they allow single mode. Okay. So I hope you understand the difference between single mode and multi-mode. Single mode is possible only for if the core size is less than certain dimension, and that diameter of the core depends on the wavelength at which you are driving the single mode. Okay. Okay. So it depends on the wavelength. So I have mentioned 8 to 10 micrometers. That is the core diameter, but it is the core diameter for the wavelength which I have mentioned there, 1550. Can be plus minus a few nanometers. For such a wavelength of operation of the system, or if you want to send signal at 1550 nanometer, then the single mode fiber core diameter is 10 micron. Okay. If you change the wavelength, the core diameter will change. Okay. What about multi-mode fiber? Multi-mode fiber has a core of much larger diameter. Now, if it has a larger diameter, it will allow other modes also to travel through. So instead of multi-mode, many more modes will travel. Obviously, the pulse dispersion is also more with multi-mode fiber. Graded index fiber allow multi-mode transmission, but it is very special. In case of graded index fiber, since the refractive index continuously changes, okay, you can trace the optical paths for different modes. It will turn out that for a certain path duration, certain spacing in the fiber, for the wave to energy to travel from here to here, the paths will be curved paths and a straight path. Okay, time taken for that curved path will be the same as the time taken for the other paths, like the minimization thing which we discussed yesterday. Okay, so therefore in graded index fiber, dispersion is reduced. It is much less than multi-mode step index fiber. However, graded index fibers are expensive. We would normally like to avoid it. But graded index fibers are very useful in making devices. Like you can use a graded index fiber to make a small lens. Okay, miniature lens. Overall diameter of the optical wire is about 120. This is standardized. Industry produces fibers with a overall diameter of 125 micron. Some special fibers may have larger diameter. Okay. So what you have is, see, the optical fiber is like your human hair. It has a diameter of 125 micron. Okay. In such a thin wire, you have a cladding as well as core. The energy travels mostly in the core. Approximately, we'll say the energy will travel only through the core. Okay. If it is a multi-mode fiber, a little bit of energy from the core can leak out as it travels further. Okay. So there are differences in what happens in a single mode fiber and what happens in a multi-mode fiber, but roughly you get the idea. Okay. Oh, my slide is gone. Internet. Okay. So microstructured fibers are of interest for us in this discussion. Here is a cartoon of fiber, optical fiber. What you have in the, see, this is the core made of glass. This is the cladding, outer part of the fiber. This is also glass. this glass is slightly doped so that its refractive index is 1% more than this. This is pure silica, but there are other ways also. You can make the core as pure silica, therefore the cladding should have a lesser refractive index. You can dope the cladding and make it. So there are different scenarios. Apart from this, it is provided a polymer coating for protection. Okay, this glass is very fine. Any scratching will create a transmission problem. So to prevent all that or environmental effect on the glass, to cover it with a polymer coating. Over that you can have other coatings. And so if you buy single optical fiber from the market, one variety is what is called as a patch cord. A patch cord looks like an ordinary electrical wire, but it has all these coatings. Okay. So as I told you, the core diameter depends on whether you want a single mode propagation or multi-mode propagation. Single mode propagation, core size is less. Multi-mode propagation, core size is more. Remember, outer diameter, cladding diameter is always fixed. That is not going to change. This is the cross section of a microstructured fiber. Okay. Previously, we had the core and cladding. Core was a homogeneous glass material. Cladding was also homogeneous.
What about this hollow core?
Yeah, I will come to that. So, this central portion is glass. This is called the core. Okay. It is as if you have the full fiber made of glass into which you have put in capillaries. Each of these can be treated as tubules, capillaries, which somehow are pushed into the optical fiber. Okay. So unlike step index fiber, here you don't have a boundary between core and cladding, as you saw in the previous case. So this is some kind of a inhomogeneous cladding. But what is that inhomogeneous? What is inhomogeneity? Because of air. In each of those smaller tubes is going to be filled with air unless you take precaution and evacuate it, make it vacuum, or fill it with some other gas. Because they are very minute, capillary means the diameter is very small, right? So it's not very easy to push something into that. So generally it is air filled. So the left hand side is called a solid core microstructured fiber, because this portion is solid glass. Here the central portion is also a tube. It's not a it's not a capillary, and its diameter of that central portion can be as much as 60, 70 micron or more. Okay. So this can be air filled. So core can be air filled, or it can, if it is air filled, it is called hollow core. You can also fill this with some gas or a vapor or even a liquid. Normally they fill it with some gas or leave it air filled. Okay. What is the difference? I will tell you. What are the other side tubes? These are all capillaries filled with air. Okay. If these capillaries were not there, then the refractive index of the cladding would have been that of glass. Now you have put in these tubules, refractive index will be altered. Okay. So obviously, depending on how many of these capillaries you put in what fashion, refractive index of the cladding will get modified. That is what we want. We want a core refractive index slightly higher than the cladding refractive index. This is another way of doing that, but obviously this is more expensive to make, and you cannot. Sometimes the overall fiber dimension may become 200 micron or 250 micron. They are not so flexible, so there are issues. Okay. I'll not go into details of how to arrive at the results which I am going to speak. We can show, see, first of all, these, capillaries are arranged in a regular fashion, geometrically regular fashion. Okay, so they are like lattice in the crystals which you study. Okay, these are tubes which are arranged in a maybe a hexagon pattern or circular fashion. That will dictate certain things about the propagation properties of the light. Where will the light travel here? It will travel through the central portion. Okay, and you can show that most of the light will go through the central portion, so that it will be behave like a single mode fiber. Okay, so this microstructured fiber typically works like a single mode fiber. What is the advantage? Dispersion is less. If it is multi-mode, competition between the modes will enhance the increase the dispersion. So that is why we look for single mode. Another thing is, so if you try to push light into, this is the cross section of the wire, it will be extend in the vertical, perpendicular, like a wire. Propagation will have, light propagation will be confined very tightly to the core. Okay. There is one more variation of this, in which you have only one layer of these capillaries. Instead of so many capillaries, only one layer around a circle, periodically arranged. That is a special type of fiber. It's called as anti-reflection hollow core fiber, AR-HCF. Okay, it is used for a specific purpose. So there are different variations of these fibers. If you read from literature, you will see come across different patterns. Okay, so depending on that pattern of the capillaries, you can achieve a level of dispersion at a particular over a wavelength range. This is another plus point for these microstructured fiber. Single mode fiber propagation, as I told you, in the case of normal fibers, is ensured for a particular wavelength or a narrow wavelength range, highly monochromatic light. Okay. If you change the wavelength, it can become multimode. The same single mode fiber will become multimode if you reduce the wavelength. Okay. Here, that single mode propagation can happen over a continuous range of wavelengths. That is another advantage. Okay. The fourth advantage is that this being a fiber, it has nonlinear properties. It has specifically chi3 type nonlinear properties. Okay. Because it's a material, when you put light into a material, what is the response? The response is dielectric polarization. You have come across D in electromagnetic theory. D is epsilon naught E plus P. Okay. That P is something which contains material interaction, because you write P as epsilon naught chi E. That chi basically depends on the material. But epsilon naught chi E is valid only at low intensities, what we call as linear optics. If you use a laser, linear optics is no longer valid. You have to bring in additional terms, nonlinear terms, which will have their own consequence. Okay. So it turns out that the solid core you can call it photonic crystal fiber, PCF, solid core PCF, hollow core PCF. So in the solid core PCF, since the core material is a solid, it will have a certain amount of dispersion, it will have a certain amount of nonlinearity, okay, and it can only withstand radiation of a certain intensity. See, what I mean is, if you shine a very high power laser onto any material, what do you expect? You must have come, see, lasers are used for many things. It will destroy that material. Okay, if the laser power is too much, it will simply vaporize the material. That is called damage, optical damage. So if you try to push too much laser power into the material, into the fiber, it is likely to get damaged. Then of course many things go wrong. Hollow core fiber, there is no material in between, it may be vacuum even, therefore no dispersion, very minimal dispersion, practically zero dispersion. Higher laser power can go through that. Okay, so that is the advantage with hollow core fiber. Okay, we will see that both solid core fiber and hollow core fiber, in particular hollow core fiber, find large applications in quantum devices. Okay. Time ಆಗೋಯ್ತಾ ಮೇಡಮ್? ಎಕ್ಸಾಕ್ಟ್ ಇನ್ನೊಂದು 5 ನಿಮಿಷ. So I have, whatever I have spoken, I have put in the slide, you can read it out. So look at the last statement, multiple core, take it as microstructured fiber. Microstructured fiber can be tailored or designed to satisfy a particular type of light guiding with minimum dispersion, single mode. Okay, so the design of microstructured fiber is also very interesting. Some of you who are doing research in this area can look at those issues. Fiber applications. See, this slide shows generally roughly what are the components in a quantum optical system. Okay, so you will see that at the top there is an all fiber photon source. Now you would have heard about photon sources being bulbs or tube lights or a laser pointer. Okay, but these are bulk devices. I want to miniaturize everything. We want to make smaller and smaller chips. 1 nanometer technology, 5 nanometer technology. Okay, why do I want to do that? Because I want to make it less, use less power for a certain thing. I mean, more efficient, lightweight, and so on. Okay, so generally there is a tendency to make smaller and smaller chips or put in more and more components into a certain size. Similar thing we want to do here also. So I don't want to use a laser pointer like this in my photonic crystal. So people have already invented photon sources which are basically made of some thin film devices and fiber. Fiber is very thin. So to that extent you have miniaturized or made it lightweight so that it can go into the satellite. So there are many angles. Okay. Apart from that, there can be a quantum repeater. What is a repeater? Takes in some corrupted signal or attenuated signal, recreates it, pushes it to the next part of the channel. Okay. Then you can have this shows a hollow core fiber filled with a vapor. What vapor? Maybe rubidium vapor. To do what? You can use it as a nonlinear material to achieve a certain interaction. You may certainly have quantum dots as either detectors or sources of photons, and so on. This indicates what is OFC, QFC, quantum frequency converter. So there are components which will change the frequency, which may be coming from here to something else. Okay. Not only do you want to generate photons at a certain frequency, you want to, maybe you want, for some purpose, you want to change the wavelength so that a certain other objective is satisfied. So this gives you a general idea of what are the different items involved in a photonic system. Okay. ಈಗ ನೆಕ್ಸ್ಟ್ ಮಲ್ಲೇಶ್ ಅವರು ಹೇಳ್ತಾರೆ. Okay. Can I then continue with this in the second lecture? I will avoid the second lecture.
So thank you, sir. We all break for the tea. We'll reassemble back by 11:40. Tea is out.
ಇಲ್ಲ ನಾನು ನಾರ್ಮಲೇ ತಗೋ